On the 24th of December 2024, while most of the planet was wrapping presents, a small spacecraft about the size of a car flew into the atmosphere of the Sun. Not near the Sun, into it. Into the corona, the outer atmosphere of a star 3.8 million miles above a surface hot enough to vaporize anything we have ever built. It was moving at 430,000 miles an hour. That is the fastest any human-made object has ever traveled. At that speed, you could cross from New York to Los Angeles in about 20 seconds. You could reach the moon in half an hour, and then, for a few days, nothing. No signal. The spacecraft was behind the Sun, inside the fire, alone, out of contact, doing the thing it was built to do or dying in the attempt. On the 26th of December, a single tone arrived back on Earth. A beacon. It meant, I am alive. I made it. I have data. That spacecraft is called the Parker Solar Probe, and the story you have probably heard about it, the story about a machine that touched the Sun and somehow did not melt, is the least interesting thing about it, because the real question was never whether it would survive. The engineers were fairly confident about that. The real question was what it would find once it got inside. What is actually happening in the place no instrument had ever been? Why is the Sun's atmosphere hundreds of times hotter than its surface? A fact that, on the face of it, should be impossible? Where does the solar wind actually come from? What are the strange magnetic kinks in the space around our star that nobody can fully explain? This is not the story of a probe that touched the Sun. This is the story of what the Sun told it back. To understand what Parker found, you have to start with a problem that is almost 100 years old, and a man most people have never heard of. In 1958, a young physicist at the University of Chicago named Eugene Parker published a paper. In it, he argued something that sounded to most of his colleagues like nonsense. He said the Sun was not sitting quietly in space, radiating light. He said the Sun was leaking, constantly, that it was throwing off a continuous stream of charged particles in every direction, at enormous speed, a wind blowing out of the star and across the entire solar system. He called it the solar wind. The reviewers tried to reject the paper. Two of them said it was simply wrong. One senior scientist told Parker to go to the library and educate himself before publishing again. The idea that a star could bleed a permanent gale of plasma into space struck the establishment as absurd. The editor of the journal, Subramanian Chandrasekhar, who would later win a Nobel Prize, overruled the reviewers and published it anyway. 4 years later, in 1962, NASA's Mariner 2 spacecraft flew toward Venus and measured the space it passed through. It did not find empty vacuum. It found a steady stream of charged particles blowing past it the entire way. Exactly what Parker had described. A constant wind, flowing out from the Sun, filling the solar system. The ridiculed idea was simply correct. The space between the planets was not a void, it was a river, and the Sun was its source. Eugene Parker spent the next 60 years as one of the most important figures in solar physics, the man who, more than anyone, taught us that the space between the planets is not empty. It is weather. It is the breath of the Sun. In 2018, NASA did something it had never done in its entire history. It named a spacecraft after a living person. The Parker Solar Probe. And in August of that year, at the age of 91, Eugene Parker sat at Cape Canaveral and watched the rocket carrying his name climb into the sky on a column of fire, on its way to fly into the very wind he'd imagined 60 years before anyone believed him. He died in 2022 before the spacecraft made its closest approaches, but he lived long enough to know it was working. He lived long enough to see his idea fly into the Sun. Here is the engineering problem stated plainly. The Sun's surface is around 5,500 degrees Celsius. The corona, the outer atmosphere Parker had to fly through, reaches between 1 and 3 million degrees. You want to send a spacecraft into that, keep its instruments at roughly room temperature, and have it survive not once but 24 times. The first thing to understand is that this is not as impossible as it sounds, and the reason is one of the most counterintuitive facts in physics. Temperature and heat are not the same thing. The corona is at over 1 million degrees. But the corona is also almost a vacuum. It is so thin, so sparse, so close to empty that there are very few particles to actually transfer that heat into a solid object. A million-degree particle that hits Parker's heat shield carries an enormous amount of energy, but there are so few of them that the total heat delivered is manageable. It is the difference between putting your hand in a hot oven and putting your hand in boiling water. The water is cooler, but it is dense, so it burns you instantly. The oven air is hotter, but it is thin, so you can hold your hand in it for a moment. Parker flies through the hot, thin oven. That still leaves the radiation, the raw, blistering sunlight pouring onto the spacecraft at point-blank range. And that is what the heat shield is for. The shield is a disc about 8 feet across and 4.5 inches thick. It is made of carbon, a foam core of carbon sandwiched between 2 carbon plates. The sun-facing side reaches around 1,400 degrees Celsius, hot enough to glow. But on the other side of those 4.5 inches of carbon, in the shadow the shield casts, the spacecraft's instruments sit at about 29 degrees Celsius, room temperature. A coffee-warm interior, 4.5 inches behind a surface hot enough to melt steel. The whole spacecraft is built around staying in that shadow. If the heat shield ever turned away from the sun, even slightly, the instruments behind it would be destroyed in seconds. So Parker carries autonomous sensors that detect the edge of the shadow and fire small thrusters to keep the shield aimed at the sun without waiting for instructions from Earth. There is no time to wait for Earth. Light itself takes 8 minutes to make the trip, and the solar panels, the very thing that powers the spacecraft, have to be partly retracted into the shadow as it gets close, because full sunlight that near the sun would cook them. The exposed slivers that remain are cooled by circulating water, a tiny radiator system bleeding heat into space. To get there at all, Parker did not fly straight at the sun. You cannot. The Earth is moving sideways around the sun at enormous speed, and any spacecraft launched from it inherits that sideways motion. To fall toward the sun, you have to cancel it. So Parker spent years flying past Venus, 7 times, using the planet's gravity on each pass to bend its path and bleed off speed, tightening its orbit like a stone on a shortening string, falling closer to the sun with every loop. 7 encounters with one planet just to fall toward another star. And what does the spacecraft actually carry behind all that shielding? 4 sets of instruments, each pointed at a different piece of the mystery. There is fields, which measures the electric and magnetic fields the spacecraft flies through, the invisible architecture of the corona. There is sweep, which catches the actual particles of the solar wind, counting the electrons and protons and heavier ions and clocking how fast they move. There is a particle detector called ISOIS, which watches for the high-energy particles the sun flings out during eruptions. And there is one camera, just one, called Whisper, peering out sideways from behind the shield to photograph the corona and the wind the others can only feel. That distinction matters more than it sounds. Every other mission to the sun before Parker was, in effect, an eye. It looked. It photographed. It studied the sun the way you might study a fire from across a room. Parker was the first to be a hand as well as an eye, to reach into the fire and feel what was there. Most of what it discovered not by seeing but by touching, by flying its sensors directly through the substance of the corona and measuring it from within. Now we come to the mystery that justifies the entire mission. The reason it was worth building a machine to fly into a star. It is called the coronal heating problem, and once you understand it, you cannot unsee how strange it is. The sun makes its energy in its core by fusion at 15 million degrees. That energy works its way outward over tens of thousands of years until it reaches the surface, the photosphere, the bright disk you see in the sky. The surface is about 5,500 degrees Celsius, hot, obviously. But here is the thing about heat. As you move away from a source of heat, it gets cooler. Move away from a campfire and you feel the warmth fade. Move away from the sun's surface, out into its atmosphere, and the temperature should drop. It does not drop. It climbs, violently. Just above the surface in the corona, the temperature is not 5,000 degrees. It is 1 to 3 million degrees. The sun's atmosphere is hundreds of times hotter than the surface beneath it. It is as if you walked away from a campfire and the air got hotter the further you went, until a few feet back it was hot enough to vaporize you. This makes no obvious sense. The energy comes from the core, it passes through the surface, and then somehow in the thin gas above the surface it gets dramatically hotter again. Something out there is dumping enormous amounts of energy into the corona, and for over 70 years nobody could prove what it was. There were two main suspects. The first is waves. The sun's surface churns and boils, and that motion can launch waves along the sun's magnetic field lines, specifically a kind called Alfvén waves, named for the physicist who predicted them. These waves can carry energy up from the surface into the corona, where they break like ocean waves hitting a shore and dump their energy as heat. That was one idea. The second suspect was Eugene Parker himself. In 1988, the same man who predicted the solar wind proposed that the corona is heated by countless tiny explosions, flares far too small to see individually, each releasing a burst of energy when the sun's tangled magnetic field snaps and reconnects. He called them nanoflares. Imagine the corona as being heated not by one furnace, but by billions of tiny matches striking constantly across the whole surface of the sun. Waves or nanoflares. For decades, the debate ran on data gathered from 100 million miles away, looking at the corona through telescopes, inferring what was happening from light alone. What nobody could do was go there, fly into the corona, stick a magnetometer and a particle detector directly into the million-degree gas, and measure, in person, what the magnetic field is doing and how the energy is actually flowing. That is what Parker was built to do, not to take a better photograph of the corona, to stand inside it and feel it. The first time Parker flew close to the sun, in 2018, it found something nobody expected, and it is still one of the most important things the mission has discovered. The solar wind, up close, is not a smooth, steady outward flow. It is violent and structured and strange. And threaded all through it, the spacecraft kept hitting sudden, sharp reversals in the sun's magnetic field. The field would be pointing one way, and then in a fraction of a second it would whip back on itself, fold into an S-shape, kink hard and snap back. Over and over, constantly. Scientists called them switchbacks. Picture a garden hose with water rushing through it, and someone keeps flicking sudden kinks into the line that travel down its length. The magnetic field of the solar wind near the sun is full of these kinks. Each one is a region where the field has folded back on itself so sharply that, for a moment, it points in nearly the opposite direction, and the plasma speeds up in a jet as it passes through. This was a surprise because the wind further out near Earth is much smoother. The switchbacks are a near-sun phenomenon. Something close to the star is generating them, and they iron out as they travel. So the obvious next question was, what makes them? And in 2021, Parker's data, led by physicist Stuart Bale at the University of California, Berkeley, traced the switchbacks back to their source. They were not random. They lined up with specific structures on the sun's visible surface. The sun's surface is divided into cells called supergranules, vast convection cells, each larger than several Earths, where hot plasma wells up in the middle and sinks at the edges. And at the boundaries between these cells, the magnetic field bunches into funnels. The switchbacks appeared to be launched from those magnetic funnels, routed between the supergranules. The 2024 follow-up work strengthened the picture further. The switchbacks are made down low, in the corona, near the sun, not produced by the long journey through space. They are born at the star and carried outward. Why does this matter beyond being strange? Because switchbacks carry energy. They are a form of the very Alfvén wave activity that might be heating the corona. They are not just a curiosity in the wind. They may be a fingerprint of the engine that makes the corona hot in the first place. Parker did not just see them, it traced them home. And here is the part that is easy to miss. No telescope could have found this. From Earth, the switchbacks are invisible. They smooth out long before the wind reaches us, ironed flat by the journey. The only way to know they existed at all was to be there, magnetometer first, in the near-sun wind, in the moment the field whipped past. The discovery did not come from a better camera or a sharper image. It came from presence. From a sensor inside the corona, recording the field reversing direction 190 times an hour. This is the kind of thing you can only learn by going. There was another prediction, very old, that Parker was uniquely placed to test. The solar system is dusty. It is full of tiny grains, debris from comets and asteroids, ground down over billions of years, drifting through the space between the planets. That dust is so pervasive that on a dark night, in the right conditions, you can see sunlight scattering off it as a faint glow in the sky called the zodiacal light. The inner solar system is, in a real sense, a haze, but for over a century physicists predicted that very close to the Sun this should stop. There should be a region, a bubble, swept completely clean of dust. Because that close to the star, the heat is so intense that the dust grains do not just get hot. They vaporize, they are destroyed, turned into gas before they can drift any closer. There should be a dust-free zone surrounding the Sun like a clearing in a forest. Nobody had ever seen it, because nobody had ever been close enough to look from the inside. Parker found it. As the spacecraft fell closer and closer to the Sun, its wide-field camera watched the dust thin out, and then, at around 3.5 million miles from the Sun, begin to clear. The haze gives way to a bubble. The dust-free zone, predicted for 100 years, confirmed at last by a spacecraft flying through the edge of it. It is a small finding next to the heating paradox, but there is something quietly profound about it, a prediction made by people who could only do the mathematics, who could never have dreamed of going to check, confirmed by sending a real object to the real place and looking with real eyes. That is the whole of science in one image. We thought there should be a clearing near the fire. We went. There was. The solar wind comes in two broad kinds, and the difference between them was one of the longest-running puzzles in the field. There is a fast wind moving at around 700 kilometers a second, and there is a slow wind moving at around half that. The fast wind, scientists had worked out fairly confidently, comes from coronal holes, regions on the Sun where the magnetic field lines open straight out into space instead of looping back down, so the plasma can stream away freely, fast and clean. The slow wind was the harder problem. It is gustier, more variable, richer in heavier elements, and nobody could pin down exactly where on the Sun it was coming from. It seemed to come from everywhere and nowhere. To trace it, you needed to measure the wind while it was still young, close to the Sun, before it had been stirred and mixed by the long journey out to Earth. Parker did exactly that. Flying through the near-Sun wind, sampling it directly, the data, again with Stuart Bale and colleagues, published in Nature in 2023, pointed to the slow wind being born at the edges, at the boundaries of coronal holes, where the open magnetic field lines meet the closed loops anchored back into the Sun. It is along those seams, where open and closed magnetic structures press against each other, tangle and reconnect, that the slow, heavy, gusty wind appears to leak out. The slow solar wind, in other words, is not a steady exhalation from the whole Sun. It is something that bleeds out of the cracks, out of the borders between two kinds of magnetic country. This is the kind of answer you can only get by being there. From 100 million miles away, the slow wind is a smear of data. Up close, inside the corona, you can watch which part of the Sun it is actually pouring out of. That is the entire point of the mission distilled. Not better pictures. Presence. In April of 2021, on its 8th close pass, Parker crossed a line that does not exist on any map but is, in a real physical sense, the edge of the Sun itself. It is called the Alfvén critical surface. Below it, the Sun's atmosphere is dominated by its magnetic field. The plasma is still bound to the star, still part of it, able to flow back and forth. Above it, the solar wind has broken free, moving outward faster than any wave can travel back, gone for good. The Alfvén surface is the true boundary where the Sun ends and the solar wind begins. Cross it, and you are inside the Sun's atmosphere in the only sense that physically matters. Parker crossed it at around 18.8 solar radii, roughly 8 million miles above the surface. For a stretch of hours, the spacecraft was inside the Sun's magnetically dominated corona. The first object ever built by humans to enter the atmosphere of a star and come back out. That was the moment that earned the headline. Parker touched the Sun. And it is a genuinely staggering thing. A sentence that would have sounded like fantasy at any earlier point in human history. We built a thing. The thing flew inside a star. But notice what touching the Sun actually meant in practice. It did not mean surviving the heat, though it did. It meant being in the right place to take measurements no one had ever been able to take. The value of crossing the Alfvén surface was not the crossing. It was the data gathered while inside, The magnetic fields, the particles, the waves sampled from within the boundary, where the corona is still connected to the star that made it. The probe did not go to the sun to prove it could. It went to listen from a place no one had ever listened before. Which brings us back to where we started, the 24th of December, 2024. By that point, Parker had spent 6 years tightening its orbit, falling closer with each loop. On that Christmas Eve, it reached its closest approach to the Sun, 3.8 million miles from the surface deep inside the corona, at 430,000 miles an hour. The closest any spacecraft has ever come to our star, matching the record-setting distance the mission was designed to reach. To put 3.8 million miles in perspective, the Earth orbits the Sun at about 93 million miles. So Parker, at closest approach, closed to about 4% of the Earth-Sun distance. If you shrank that distance down so the Earth and Sun were 1 meter apart, Parker would be skimming about 4 centimeters above the surface of the star. That close. Through the corona, at 120 miles every single second, and consider the speed for a moment longer because the number is hard to hold, 430,000 miles an hour. The fastest bullet a rifle has ever fired travels at about 2,000 miles an hour. Parker, at perihelion, was moving more than 200 times faster than a bullet. A signal of light leaving the spacecraft takes about 8 minutes to reach Earth. Parker itself, in that same 8 minutes, sweeps across more than 50,000 miles of its orbit. There has never been anything we made that moves like this. It is the closest a human-built object has ever come to the speed of the things the universe makes on its own. The heat shield on that pass was expected to climb toward 1800 degrees Fahrenheit, close to 1,000 degrees Celsius, while the instruments behind it stayed at room temperature, doing their work. And during those hours, out of contact behind the Sun, the spacecraft's only camera, an instrument called Whisper, kept its shutter open and recorded the closest images of the solar corona ever taken. Then it went quiet, and on the 26th of December, the beacon came home. In July of 2025, NASA released those images, and they showed something extraordinary. Not a still, calm corona, but a corona in motion, the solar wind streaming outward in real, resolved structure, and within it, coronal mass ejections, vast eruptions of plasma, captured colliding with one another and merging into larger, more complex structures as they barreled out into space. We had modelled this happening. We had never watched it happen, this close, from the inside. The images also let scientists trace one of the most important boundaries in the solar system, the heliospheric current sheet, the surface where the Sun's magnetic field flips from one polarity to the other, closely tied to that slow, gusty wind. And rather than the neat, flat plane of the textbooks, the close-up images revealed it for what it really is up close. A thin, warped, folded, rippling surface, far more dynamic and structured than anyone could see from far away. This is what flying into the Sun brought us. Not a photograph from a tourist distance, a view from inside the weather, looking at the machinery of a star turning over in real time. It would be a tidy story if Parker had flown into the corona and solved the heating paradox once and for all. It did not, and the honest version of this is more interesting than the tidy one. What Parker did was narrow the answer. Before the mission, the heating debate, waves versus nanoflares, was argued from a distance with limited data. Parker went and measured the corona from within, and what it found does not crown a single winner. It points to both. The Alfvén waves are real, and they carry energy, and the switchbacks Parker traced back to the Sun appear to be part of that wave activity. The latest work, around 2024, on a particular small-scale form called kinetic Alfvén waves, finds them consistent with what Parker and Europe's solar orbiter are measuring, a genuine channel for dumping wave energy into the corona. At the same time, analysis of the nanoflare idea suggests the tiny reconnection bursts, on their own, are probably not frequent enough to do the whole job. The corona, the current picture says, is most likely heated by a mixture. Waves dissipating their energy in some regions, magnetic reconnections sparking in others, the balance shifting depending on where on the Sun you look. That is not failure. That is what real answers usually look like. The universe rarely picks one clean mechanism. Parker took a 70-year-old mystery argued from 100 million miles away and turned it into a quantitative problem argued from inside the corona, with numbers, from the actual place. The remaining uncertainty is sharper, smaller, and far better defined than it was, and the mission is not over. Parker continues to loop the Sun, gathering data through 2025 and beyond, every pass adding to the record from the one environment in the solar system we had never been able to reach. The corona is still giving up its secrets one orbit at a time. Step back from the data for a moment and look at what actually happened here. A man sat down in 1958 and imagined that the Sun was breathing a wind across the solar system and was told he was wrong. 60 years later, his country built a machine, named it after him, and flew it into that wind while he watched. The machine fell toward the Sun for 6 years, slingshotting past another planet 7 times to lose the speed it needed to lose. It carried 4.5 inches of carbon between a surface hotter than molten iron and a set of instruments sitting at room temperature. It crossed the invisible edge of the Sun's atmosphere and survived. And then, on a Christmas Eve, it dived deeper than anything ever had, lost contact and came back with images of a star's atmosphere tearing itself apart from the inside. It found the kinks in the wind and traced them to the surface. It found the empty zone where the dust burns away. It watched the slow wind leak out of the seams between magnetic worlds. It narrowed a 70-year paradox down to a sharper question. And it did all of it from inside a place we had only ever been able to look at, never enter. The Greeks had a story about a boy named Icarus, who flew too close to the Sun on wings of wax and feathers and fell when the heat melted them apart. It was a warning. There are limits. Do not reach beyond them. Do not approach the things that can destroy you. Parker is the answer to that warning, written across 2,500 years. We did approach the thing that can destroy us. We approached it on purpose, with carbon instead of wax, with engineering instead of arrogance, and we did not fall. We flew into the corona of a star and we came back with the data. The wings held. There is something worth sitting with in that. Not the survival, the curiosity. We did not fly into the Sun because we had to. There was no threat to escape, no resource to claim. We did it because we did not know what was inside the corona, and not knowing was, in the end, unbearable to us. So a species of small animals on a small planet built a thing that could touch a star, and sent it, and waited in the dark for the beacon to come home. It came home, and it brought back the unknown, turned slightly more known. That is the whole of it. That is what Parker found inside the Sun's corona. Not just switchbacks and dust-free zones and the birthplace of the wind, though it found all of those. What it really found is the thing we always find when we finally reach a place we have only imagined, that the real thing is stranger, more violent, and more beautiful than the picture we drew from far away. If a story about the only spacecraft to ever fly into a star is the kind of thing you want more of, you know what the subscribe button is for.